Yeah, hi everyone. So we are back in our session, right? So this is going to be lecture number 4 on communication system. And as we know that communication system is one of the very important subjects. So from the last 3 sessions, I have covered some of the basic things which is needed, in communication system like sync function, Gaussian function and all. But in this session, I'm gonna start the analog communication, right? You can say like I will start analog communication, okay? And you should be familiar with the basic thing like what are the basic requirement, what are the basic resources of communication. They are bandwidth and power. And at times you will also see the signal to noise ratio and all, right? So many things we will discuss, right? In communication system, there should be one transmitter, there will be a channel, and there will be a receiver. These three basic components you have to keep in mind, right? Always. So I'm not discussing those things, in detail because they are not that important. We have to be very exam oriented now because at the time is like we have got only 100 days, you can say. So we will be focusing on exam point of view, right? Okay. So yes. So I have told you that why do we find the why do we go for Fourier transform, right? Understood. So we go for the Fourier transform just because to understand the to know the frequency content of the signal, right? Okay. And we always try to keep the bandwidth of any signal should be pretty low, okay, and the channel bandwidth should be very high, right? So those things you have to keep in mind, right? So basic resources are power and bandwidth, right? So we talk about Fourier transform, okay, to understand, to know about the frequency content of the signal so that you can decide the bandwidth of the channel, right? Okay, that is very important. Yeah, hi Raviteja, good afternoon. Yes. Yes, certainly Raviteja, we will try, okay, certainly. Okay. So this is very important, right? So communication system, right? Yeah, 2.5 hours or 3 hours. Yeah, I'll try, right? So, okay. So you have to always keep in mind that the signal bandwidth, right? The signal bandwidth should be, you need to keep minimum, right? Okay, so that you can send many signals. Okay, you can send many signals through the channel, and the channel bandwidth, right? And the channel bandwidth, you can keep maximum, right? Okay, maximum. These are these are some normal strategies that you have to follow always, right? Okay, so that you can send many signals, and if you're sending many signals simultaneously, that is called multiplexing. Okay, so simultaneous transmission of a different signals, you can say, that is called multiplexing. We'll see that, right? So what are the basic signals that we come across in our communication system? Like what are the messages, what will be the form of the messages you communicate, right? You send your voice, send your audio, or you can say you send your video or data, right? Some data, amount of data you send every day. So a lot of communication is going on around you, that is known as human communication, right? So 90% is there, right? So if I talk about what are the frequency range for you can say voice and for audio, right? Okay, and for video, right? And for and what is the difference between this voice and audio, right? So if you capture your voice in recorded form, right, so the frequency you can increase or decrease, right? That is up to you, right? And video and some form of data, right? Like computer needs data, okay, to communicate. Okay, so voice, what is the range here? Voice has got 300 hertz to 3.5 kilohertz, right? Okay, so where do we use this voice? How we transmit this voice? Using some telephone, right? In telephone, this is important that you have to keep in mind. And audio, you can say from 20 hertz, right? 20 kilohertz, right? Do you see the difference between voice and the audio? Okay, so audio is nothing but what you just record it. Okay, you record your speech, right? So that is why the range of frequency is, you see, from 20 hertz to 20 kilohertz, and the video is nothing but having the frequency range from 0 to 4.5 megahertz, right? It needs more bandwidth. And the data, data, how do we calculate the range of frequency? You can say, how do we calculate that? Okay, for data, any data. So in future, data will be basically, we'll see data in digital communication, right? So data will be represented in the form of pulses, right? So pulse width is going to decide the bandwidth, right? The pulse width, okay, pulse width. Okay, so what how do we calculate this pulse width, and how do we model this data to pulse? All these things we'll see. So pulse is very important, and I think everybody is familiar with the pulse. What is the Fourier transform of pulse, or if pulse is given in frequency domain, so what can be the equivalent of this in time domain and all, right? So please remember that. Okay, so this data basically needs a lot of bandwidth, so you can say that what we use in internet, right? Internet, right? Okay, audio basically used in radio, okay, in radio, and this is in televisions and all, right? All these things, yeah, fine. So it is very important, right? So you know that there is a transmitter, we call it transmitter here, right? And there will be a channel, you can say there will be a channel, right, through which data will be transmitted, and there will be a receiver. Okay, so before you send your signal to channel, okay, before you send your signal, okay, you need to prepare your signal, okay, you need to prepare your signal, or you can say you need to prepare your message, right? You can't directly send your message signal to through the channel and then it reaches to the receiver. ऐसा नहीं है. You need to prepare it. What kind of preparation you need, right? So there are various requirements. First of all, you need to keep your signal at low bandwidth. First of all, right? The signal should not have huge bandwidth. Okay. Otherwise, what will happen? You cannot send the signal you cannot send many signals, right, to the channel. Okay, that is one thing. And you need to also keep in mind that if so now we want to keep our message signal at very low bandwidth, right? Very low, minimum frequency, right? Minimum bandwidth. So then what problem you're going to face, right? Okay, the problem you're going to face is in this transmitter there will be an antenna also, right? There will be antenna kind of thing, right? You see there is an antenna. Okay, if the frequency is low, okay, if the frequency is low, okay, please keep in mind, if the frequency is low, then the height of the antenna is going to be very large, right? Then the height of the antenna is going to be very large, because antenna height is proportional to the you can say wavelength, right? And wavelength is inversely proportional to the frequency, right? If the frequency is low, the antenna height is going to be very high. That is one problem. So you cannot realize the very height very big antennas, right? Nowadays you can see there is in fact antennas are not visible nowadays. Tiny antennas are there, like in mobile phone and so on and so forth, right? You will not find any sort of antenna. You can see here, like this is a mobile phone, and you can see there is no antenna inside this, right? Okay, okay, so you can imagine, okay. Otherwise what will be there? Earlier we used to have a mobile phone and there used to be some sort of antenna, like nowadays in radio. Okay, uh, whatever transistor we buy, I'm talking about that radio, right, where we hear news, and in my days I used to hear commentary and all from the crickets and all, right? So you can understand, so there used to be antenna, right? Okay, and at one particular place I used to get a message, I used to get a signal, right? Okay, now I'm able to hear proper voice of a commentator, right? So but nowadays has got changed. Now the progression is happening, okay, development is there. So how can we solve this problem? Okay, this is a problem, this was a problem earlier, right? So what you can do here is you can take your message signal which is at low frequency, or you can say which is at low bandwidth. Okay, the message signal will always be having low bandwidth. Okay, okay, base band signal, sometimes we call it base band signal, याद रखना, ठीक है? अब क्या होगा? Then what we bring, we will bring some sort of carrier, right? And carrier is nothing but having high frequency. Okay, so what we will do, we'll take message signal and the carrier signal and we'll multiply them, right? Okay, we'll multiply them. So carrier will be in the form of, you can say, cosine or sinusoidal or exponential, right? Okay, according to message signal, the carrier amplitude is going to vary then, right? Or according to the message signal, carrier frequency is going to vary according to the message signal. You know, we will see according to the message signal, the amplitude of the carrier is going to vary, right? Or okay, so all those things we are going to see, right? This is very important. Please remember. Okay. So we will see different types of modulation. So this is the need of modulation. Okay, if I talk about what is the need of modulation, the need of modulation is nothing but there are various reasons that I will list down, right? So, and I will also define the modulation. What is that modulation, right? Need of modulation. Need of modulation. So though these things are not required, guys, these things are not asked in the gate examination, but you should know in brief, है ना? The need of modulation क्या होता है? Need of modulation, why you are multiplying carrier signal and the message signal, okay, so that you can translate your message signal to high frequency, right? आपको पता है in signal and system, if you multiply exponential with the time domain signal, or if you multiply cosine with the time domain signal, right? So what will happen? Translation will happen in the frequency domain, right? Modulation property from the Fourier transform that I have taught. Okay. That is just a modulation, translation in frequency domain from low frequency to high frequency. And why we are translating that low frequency to the high frequency? So that the antenna height can be, to increase the frequency so that antenna height can be realized. Okay, I mean, otherwise physically it won't be possible to realize high dimension antenna, right? So the number one point that I can list down is to reduce the size of the antenna, right? To reduce the size of antenna. Okay, to reduce the size of antennas, second one is the multiplexing. Multiplexing, right? What is this multiplexing? Multiplexing is nothing but, what is this multiplexing? Okay, multiplexing is nothing but simultaneous transmission of many signals, right? If there is no modulation, then antenna height you cannot realize. Okay, then what you have to do, you have to keep your signal at high bandwidth, right? So you cannot send many signals then, because channel bandwidth will also be limited, not like you can send many signals, right? So if the signals are having low bandwidth, okay, so you can send many signals at the same time. So simultaneous transmission of a signal, okay, having minimum bandwidth to a channel, right, is called the multiplexing, and channel bandwidth should be maximum, right? So that is the requirement that you have to keep in mind, right? So multiplexing will help you understand few things, right? Okay, please remember this. Okay, so signal bandwidth you need to keep signal bandwidth you need to keep minimum. Okay, channel bandwidth you need to keep maximum. And signal to noise ratio, okay, should be greater than 1, right? Should be far greater than 1, right? Signal to noise ratio. Okay, you will see what is this noise. Okay, noise is one of the common mode devil that you have to understand. Its need of the modulation is not at all required, okay, to understand for gate examination, right? Because in gate they will not ask need of modulation, right? So need of modulation also resolve the to you can say to reduce the effect of noise, right? So many things. Third, fourth, you can say, to overcome the okay, yeah, okay, and convert a wideband signal, okay, convert a wideband signal into a narrowband signal. Convert wideband, okay, signal to narrowband signal. Okay, narrowband signal. What is the meaning of wideband and narrowband, right? If the signal is wideband, okay, so you can convert into narrowband. You can band limit the signal, right? Okay, understood. So this is very important to understand. Okay, so convert wideband signal to narrowband, right? These are some requirements that you have to understand. So I'm not talking about noise at this moment, because if I will talk about noise, then you might get confused. What is this noise, right? So guys, as I said you, simple math we can do quickly, right? So as we know that lambda is nothing but c by f, right? If f is increasing, so lambda is going to decrease, right? Lambda is going to decrease, and this lambda is nothing but what? Height of the antenna is proportional to lambda. Okay? Like you might have heard about antenna of having, you can say half wavelength antenna, quarter wavelength antennas, lambda by 4, lambda by 2 antennas. So the dimension, or you can say the height of the antenna, is measured in terms of lambdas or wavelength. So here the height can be, as minimum as possible, right? So you can say if the like if you talk about FM 88 megahertz to 108 megahertz, and the frequency is pretty high here, right? If the frequency is pretty high, then the height of the antenna is going to be low. That is very important to understand, right? So before you send a message signal, okay, before you send a message signal, you need to prepare your message signal, right? You need to prepare your message signal. You need to eliminate noise if it is present in the message signal. You need to keep your message centering around 0, right? Matlab, so that your signal contains minimum bandwidth, right? Okay, the bandwidth should not be more, okay, in the signal, right? Otherwise multiplexation is not possible. तो आपको तैयारी करना पड़ेगा, ऐसा नहीं है कि डायरेक्टली यू जस्ट टेक द सिग्नल एंड सेंड इट, राइट? नो, यू नीड टू प्रिपेयर इट. So modulation is one of the first strategy that you have to do, right? That is you have to do. Fine. So bandwidth should be minimum, right? The signal bandwidth should be minimum, okay? And so many things are there, right? Okay. So we have already discussed the Fourier transform, right? Already we have talked about Fourier transform. The basics of Fourier transform we have covered, right? So okay. So what was the need of Fourier transform, guys? Need of FT, if I ask, need of FT was to determine the frequency content in the signal, right? Okay, to determine frequency content in the signal, right? Okay, so that you can decide the bandwidth of a channel. Okay, so all these things are there, you have to keep in mind, right? And fine. So see, I have told you how to compute, how to find the Fourier transform of sinc function, okay, and so on and so forth, right? So if the signal is band limited in time domain, suppose signal is band limited like this, right? Okay, it has a pulse width of 1 millisecond, right? Okay, it has a pulse width of 1 millisecond. You can say this t is nothing but one millisecond, right? So if you take the Fourier transform of this, okay, if you take the Fourier transform of this, okay, if you take the Fourier transform of this, so it is band limited in time domain, right? So it should not be, it will not be band limited in frequency domain. Okay, that is very important to keep in mind, right? Theoretically, if this pulse you see, if you see this pulse, this is the ideal pulse, guys, I'm telling you, right? This kind of pulse you will find in digital communication, right? So if this is a pulse, if I ask you what is the bandwidth of this signal, what is the bandwidth of this signal, so you will certainly find the Fourier transform of that, right? The pulse has got the Fourier transform as a sinc function, and theoretically sinc function has got infinite bandwidth. Okay, so if somebody asks bandwidth theoretically, right? Theoretical bandwidth is going to be infinite, right? And the practically the bandwidth is going to be what? 1 by t. Okay, I have told you also one thing, okay, remember. So suppose any pulse is given of having 1 millisecond duration, if someone is going to ask you what is the bandwidth of this pulse, so you need to find the Fourier transform, like, okay, so this should be the, like, you can say it will be 1 kilohertz, right? So 1 kilohertz. So what is this bandwidth? So bandwidth is nothing but 1 kilohertz, right? So you can say that here the 90%, 95% energy is going to contained in the frequency domain signal, right? So this is a pulse. If you find the Fourier transform of that, okay, so you will get a sinc function, right? And sinc function theoretically has got infinite bandwidth, right? It is, okay, as I told you, limit is band limited, time limited in one domain correspond to expansion in one another domain. At the same time, they cannot be time limited as well as band limited. Okay, please remember, right? But what we are doing is we are approximating, because sync function is what? Sync function, if you take a look, sync function has got theoretically infinite bandwidth, but practically we have to focus on practical bandwidth, right? Where the 95% energy is contained in this lobe, right? If I draw the actual pictures, you will find this kind of picture, right? Yeah. Gradually it becomes, okay, please remember this, right? So null to null bandwidth we try to find. Okay, so this is again the null, this is the bandwidth, actual bandwidth, right? Okay, of a signal. But if they are asking null to null bandwidth, so it will be 2, okay, 2 kilohertz. Okay, null to null bandwidth. Okay, fine. So this is one thing. Okay, suppose your signal is like this. Okay, narrow, it is very, having 1 microsecond. If someone is going to ask you what will be the bandwidth of this signal, can you find the bandwidth of this signal? You will say yes, I can find the bandwidth of this guy, right? So what will be the bandwidth of this guy? You can say the bandwidth is going to be reciprocal of the duration, right? 1 megahertz. Okay, 1 megahertz, right? Okay, 1 megahertz. Okay, please remember this. So time limited, it is narrow here, right? Narrow in time domain, and the bandwidth is going to be more, right? In this case. Okay. So I think this is clear how to find the bandwidth of a signal, right? You can easily find out the bandwidth of a signal. Okay, and suppose we consider one more signal that is nothing but, I think everybody knows, this is t equal to 0. So here the amplitude is infinite, or height is infinite, you can say, and the width is 0, right? Height is infinite, width is 0. It is an impulse, right? Impulse. So if you try to find the Fourier transform of this, right? The impulse has got a Fourier transform containing all the frequency, right? Containing all the frequency, you can say you will get one for all the frequency. Here. So what is the bandwidth here? Bandwidth is going to be infinite in this case, right? And this signal cannot be generated in the lab, that everybody knows, right? Impulse is approximated one, right? We can't generate in t equal to 0 second, we can't generate infinite force, right? आपको याद रखना है, infinite force we can't generate. Okay, so I think this is clear for you, right? Okay, fine. So frequency shifting property and the modulation property, that you have to remember always, because we will talk about modulation. Okay, so frequency shifting and or you can say modulation property, or modulation property. Okay. So frequency shifting or modulation property, you know that one more thing I'll say here. I'll say suppose you have got okay, suppose you have got cosine and some time domain cosine is there. So how many impulses will be there in frequency domain, that you should know. Okay, so the moment you see cosine, you should be able to draw the picture. Okay, you should be able to draw the spectrum of that, right? So this is important, right? Suppose you have got a signal, you can say gt is a signal whose Fourier transform is going to be g of f, right? Or g of omega, you can say. So if you multiply this gt, okay, you can say gt is nothing but a massive signal. Okay, or you can say information bearing signal, right? And you need to do modulation, right? So what you will do, you will multiply carrier signal with the massive signal. Okay, carrier signal with the massive signal, right? So what you will get, आपको ये समझना है, right? So this massive signal gets translated, okay, in the frequency domain. So first of all, you need to find the Fourier transform of massive signal, then it gets translated. So gt times cos 2 pi fct अगर करते हो fct, right? Okay, this is nothing but what? The carrier. This is nothing but carrier, or you can say this fc is nothing but carrier frequency, right? This fc is nothing but carrier frequency. This fc is nothing but carrier frequency. So if you're going to translate, if you're going to multiply this, right? So what will happen if I write in frequency domain? So it will be 1 by 2, right? 1 by 2 delta f minus fc plus delta f plus fc. Okay. Okay, so there will be two impulses, you can say, right? There will be two impulses. One impulse is at f equal to minus fc, and one impulse is at f equal to fc, right? Okay, so these are the two impulses that you will get, and height is 1 by 2, 1 by 2. Okay, I think this is clear, right? So please remember these points. These points are important to keep in mind. Okay, understood. So carrier frequency is nothing but high frequency signal. Okay, sinusoidal signal, you can say. Okay, and you can take the example of FM, right? Like 88 megahertz to 108 megahertz, right? In radar, gigahertz, right? So many things are there. Okay, so I will always consider massive signal in frequency domain, right? So please remember these are the some important structure that you have to keep in mind, right? Some important structure, like suppose I give you the signal of in time domain, it is time limited, okay, and this is the width of the pulse, okay, that is 1 millisecond, right? 1 millisecond, yeah. And having a as a magnitude, right? Height of this is g of t. Whose Fourier transform if you take, right? Whose Fourier transform I'm going to take here. So guys, I'm not going to consider entire spectrum of the massive signal, right? I'm just going to consider the particular up to which it contains more energy, right? So I'm going to consider main lobe, है ना, जो smaller lobes है ना, तो उसको हम neglect कर देंगे. तो इसका जो bandwidth आएगा, I think everybody can mark here. This is nothing but 1 kilohertz minus 1 kilohertz. If someone is going to ask you what is the bandwidth of this guy, bandwidth is nothing but 1 kilohertz, right? Bandwidth is nothing but 1 kilohertz. Please remember. Okay. So if you directly send this signal, guys, this is nothing but g of f. This is a massive signal, okay? If you directly send, this is approximated one, right? Not actual. Approximated one. Okay. So if you directly send this signal, okay, so what will happen? Life is very tough, okay? You cannot send directly this signal, okay? Understood. So you need to multiply with the carrier, right? So this is the signal here, and if you multiply this with the carrier looks like mathematically, if you write carrier, so carrier is nothing but a cosinusoidal, so whose amplitude is constant at this moment, right? So here this is a carrier means high frequency, okay? Yeah. This is high frequency signal, right? Okay, please remember, right? You can say this is nothing but cos 2 pi fct, right? And you're multiplying with gt, okay? You're multiplying with gt. So what will happen? See, you're multiplying this signal gt with the cos 2 pi fct. So this entire spectrum, the massive signal spectrum, is going to get shifted, right? Your massive signal spectrum. This is the spectrum, right? You can say any shape, any. See, shape is not important here, right? Please remember, this shape is not at all important here. You just take this is g of f, and 0 to 1 kilohertz, right? And this is 1 minus 1 kilohertz. This negative frequency is not important at all here, right? When you are talking about massive signal. Okay, so this negative frequency is just for the sake of understanding, right? Please, okay, consider. So, but the actual bandwidth of this massive signal is 1 kilohertz. कैसे मिला हमें? How we have found out this massive signal bandwidth? By just taking the inverse of the pulse, inverse of the duration of the pulse width, right? Okay, so whatever pulse was given, the duration of the pulse, okay, we have taken the inverse. We got this bandwidth in hertz, right? Hertz. So mathematically, what you're doing, you're doing multiplication by cosine, right? Okay, but pictorially, what is happening here is that your massive signal is going to get shifted now. Your massive signal is going to get shifted like here, right? It will be shifted to fc, okay, plus fc and minus fc, right? याद रखना, if you multiply cosine with the massive signal, keep in mind this, if you multiply massive signal with the cosine, so your cosine is your massive signal is going to get shifted, okay? This is called translation in frequency domain, right? This is called modulation, okay? This is called modulation, right? But you're not able to decide whether it is an amplitude modulation or what kind of modulation, right? It is simply a frequency translation, right? It is shifting, okay, your Massive signal which is at low frequency, right? That is called baseband signal. From baseband to the band pass, baseband to band pass. Okay, low pass signal. Your signal is low pass here. Low pass means the frequency is having, the signal is having low bandwidth. Okay, but now what you're doing, you're translating your massive signal to, कैसे translate कर पा रहा है? You're multiplying in time domain by cosine, right? आप कोसाइन में मल्टीप्लाई करवाते हो तो फ्रीक्वेंसी डोमेन में क्या होता है, योर मैसेज सिग्नल इंटायर स्पेक्ट्रम इज गोना शिफ्टेड एट एफसी एंड माइनस एफसी. ये यहाँ पर शिफ्ट हो जाएगा, यू कैन से एट एफसी एंड इट इज माइनस एफसी, राइट? ओके, understood. So you can say that here, suppose this is 80, right? 80, the magnitude is 80 here. Okay, this spectrum has a amplitude, you can say 80, right? If it is a sinc function, right? So 80 at here, this is at f equal to 0, it is 80, right? So but now since you're multiplying this with the cosine, I mean you're not multiply this with the cosine, you're multiply this with what, you're multiplying that with the time domain, right? So multiplication in time domain correspond to what, convolution in frequency domain, right? So that is the reason it is getting shifted. Okay, please remember. Okay, so kya, keep in mind that multiplication in time domain correspond to convolution in frequency domain, but directly we are saying we are removing the discussion about convolution in between, right? But there is an intermediate process also, right? Okay, this translation has got some process here, right? First of all, what is there, you need to take the convolution, you need to perform the convolution with gf and the impulses, right? So that impulse is going to shift, okay, your spectrum, your massive signal spectrum, right? So please remember this, there is a step involved in between, right? But we don't have to think about that, right? Since we know the property, we can go ahead, right? Okay, so this is the shift here. Now your amplitude also gets like it will be 80 by 2. Okay, so you have to take care of everything, right? So this suppose this is a massive signal bandwidth fm, you can say this is minus fm, right? So you can say this is nothing but fc plus fm, right? And this is fm fc minus fm, right? Okay, fc minus fm, fc plus fm, fc minus fm, right? And here you have to take the just what you can do, you can say that this is minus fc here, right? So we are shifting to the minus fc, you add here minus fc, okay, plus fm, so it will be fm minus fc, right? And if you add here, right, so minus fc minus fm, so it is minus fc minus fm, that's it. So I think this is clear, right? Okay, so minus of this will be here and minus of this will be here. Okay? This is what, and minus of this is going to be here. Okay, so if you want to write here, so suppose this is fc, so here you write minus fc. If you write here fc plus fm, so you write here minus fc minus fm, minus of that. If you write here fc minus fm, so you should write here minus fc plus fm. Okay, this is the situation that you have to remember, right? So what you're doing simply is if you're multiplying in the time domain, guys, okay, if you're multiplying gt in with cosine 2 pi fct, right? So what will happen here is that this gt has some sort of a, you can say this kind of a waveform, you can say it doesn't matter, right? You can say the magnitude is a here. Okay, this is fm, right, minus fm. Okay, so if you're multiplying this guy, this is a band, this is nothing but a spectrum of a massive signal. Okay, spectrum of massive signal, right? And remember, your signal is real valued signal. Your signal is real valued, okay, real valued signal. And this is a band frequency of the spectrum of the massive signal. Okay, so time domain signal is given, you have taken the Fourier transform. Now you are multiplying that in time domain only. So what is the Fourier transform of this cosine? The Fourier transform of this cosine, right? So you have to take then the convolution with the cosine. Cosine is nothing but fc 1 by 2 minus fc, sorry, plus fc 1 by 2, right? You have to take the convolution of this and this, right? So this will result what? Simply a shifting of your spectrum. Okay, plus fm, fc minus fm. Don't talk about this. You can talk, right? Okay. So convolution with the masses signal, right? Few points you have to note down. Convolution of frequency domain, sorry, convolution of masses, you can say gf with impulse, okay, in frequency domain only. What is this? Always keep in mind this will be shifting, okay? This will shift, okay? It is nothing but translation. This is the property of the, let's say this is the frequency translation. Okay, frequency translation, right? Okay, at fc and minus fc. Okay, if cosine has got fc and minus fc, right? Please remember this. So in fact, sampling process is also there, right? Whenever you want to do sampling, okay, so what you do, you multiply, the time domain signal with the impulse directly, right? Impulse, okay. Okay, in time domain you do all those things, okay? But if you multiply in time domain, so in frequency domain, what will be there? That you have to understand. That is convolution, okay? So all these things are there. These are very important concept, right? So I will talk about sampling separately, but modulation kya hota hai, I think this is important to understand, right? Okay, so now understood this. So what are the definition of modulation? If I write modulation definition of modulation, okay, as a summary, if I write, okay. So आपको ये picture continue होनी चाहिए, right? In F domain, I'm talking about F domain. Please remember, okay? If I'm talking about omega domain, then we have to be little careful. In F domain, we have to be careful, right? In both domains, right? So here you see the x-axis, that is in frequency F, hertz. Most of the time in gate examination, they will ask in hertz only because we are very comfortable with dealing with radian per second. ठीक है, so आपको समझना है. What is the definition of modulation? तो पहली definition आप बोल सकते हो process of converting low frequency signal into high frequency. Okay, process. It's a process of converting low frequency signal to high frequency. You can say from baseband to band pass. Baseband to band pass. Okay, baseband किसको बोलेंगे? When signal will be centering around origin, right? You can say around zero frequency. That is called baseband. Okay, that is the band limited signal, right? Band limited. We will limit the band. Okay, before we send the signal, we need to limit the signal, right? Okay, why we want to limit the signal? So that the bandwidth of the signal will be very low, right? Okay, and we don't have to worry about outside of that outside of that range, right? Okay, understood. Please remember that. And process of frequency translation. Okay, process of, the other definition that you keep in mind, frequency translation. Process of frequency translation, process of converting low frequency signal to high frequency signal. Fine. I hope this makes sense to you. So process of converting low frequency signal to high frequency, process of frequency. Okay, so you can solve any question then. Take Brock's book, okay, you can solve any question if you know these concepts, right? I will solve all the question with very less time you see in communication system, that I can assure you, right? The process of frequency translation means what? The spectrum of the signal shifted from low frequency region to high frequency region. That is called the okay. So low pass signal is getting converted into band pass signal. That is also one of the definition that you can see. Low pass signal is going to band pass signal. So right. So whenever you will see like MT times cosine 2 pi FCT. So you don't say this is a low pass signal, okay? It's a band pass signal, right? It's a band pass signal. Please remember this, okay? If you multiply any massive signal with the cosine, right? So that is going to be a band pass. Sometimes, you know, there is one concept called Hilbert transform, right? So sometimes they ask what is the Hilbert transform of band pass signal, like MT time cosine 2 pi FCT, right? So people don't know how to find the Hilbert transform of product of low frequency signal and the high frequency signal, right? I will tell you. It's a very important concept, right? Finding Hilbert transform of product of low frequency signal and the high frequency. It's a new concept, and you will learn something new from there, right? When we will talk about complex envelope and you know, so many things. So please remember these are the definitions, right? Okay. And one more definition that you have to remember is the fourth one. Process of converting wideband signal into narrowband. Process of converting wideband signal to narrowband. Right? Narrowband. You know, band pass signal will be narrowband. Okay, just okay. So this is very important. These are the definitions that you can talk about, right? If someone is going to ask you. Okay. Now, what is wideband signal and what is narrowband signal? That we need to understand. When we can say something is wideband signal. Okay, if the ratio of high frequency and the low frequency is far greater than 1, that is called wideband signal, right? If the ratio of high frequency, okay, to the low frequency, right, okay, is far greater than 1, that is a wideband signal. Please remember this. Okay, and what is this narrowband signal? Narrowband signal, you know, you will find narrowband and wideband, okay, in FM. When we will talk about frequency modulation, right? So there is a FM is two kind, right? Two type of FM will be there: wideband FM, narrowband FM, right? So we'll see when we can say narrowband FM. We will see when we can say wideband FM in that case, right? अभी तो बस इतना है कि what is this narrowband, what is this wideband? So narrowband is nothing but if you take the ratio of high frequency to low frequency, it should be close to 1. That is called narrowband. Okay, not far greater than 1. Right? Okay, so suppose I take one question here like audio. Suppose example I'm taking audio. Audio has a range like, you know, 20 to 20 kilohertz. Now we need to decide whether it is narrowband signal or a wideband signal, right? So okay. Narrowband signal or a wideband signal, okay. If you take the band also, right, if you like recently one of my my grandfather asked me you know, to send one transistor for him, right, like one radio to hear the news and so on and so forth. So I was thinking, like he said to me, double band radio he needs, right, double band radio. So I was thinking, what is this, right? You know, we are engineer, but still we are glued, okay, we are insane about solving questions. We don't care about what's happening around us, right? So then I understood that, okay, he's asking about AM and FM, two bands are there, right? Or okay, AM and FM. Now which one is Wide band, which one is narrow band? That you have to keep in mind, right? So this is what if you take the ratio of high frequency, which is 20 kilohertz, right, upon the low frequency, that is 20. Okay, so it is nearly, you can say, 20 gone, right? So 1 kilohertz, right, around 1000 hertz. So this is a very high frequency, right? Okay, you can say that it is a wide band. It's a wide band, okay, situation. ठीक है? So as I told you that you need to understand only the Fourier transform of cosine, right? So if you, I have already told you what is that cosine 2 pi fct, right? It has a Fourier transform. So I will directly depict this, right? Picture. One guy is at fc, one guy is at fc, right? 1 by 2, 1 by 2. Okay, this is in f domain. This is in f domain. But if I talk about in omega c domain, to cos omega ct, right? What we can say here, it is going to be, suppose this is omega, it will be omega c, and this is at minus omega c, and this is going to be pi and pi, pi and pi, please remember, right? Okay, so because it has got pi times of delta omega minus omega c plus delta omega plus omega c, right? So whenever one cosine is present means what? If there is one cosine, right? So there will be two impulses. ये याद रखना. These are very important things, right? So cosine, if cosine in time domain looks like this, okay, in frequency domain, right? Or you can draw also. Cosine is nothing but high. This is a carrier frequency, so it is having very high, situation, very high frequency. Very high frequencies. This pictorially, if you realize, right, in time domain it has high frequency like this, okay, but in frequency domain there are two impulses, okay. I think this is clear. So what are the important what are the important notations, or what are the name of that message signal and all? What are the different names of them, right? I'm just going to talk. So please remember these things, okay? These things are important for you. So only single frequency is there. That frequency is nothing but so some notations and terminologies that I'm gonna talk now. So suppose we have got the message signal MT. MT is nothing but a message signal. Message signal. Sometimes we call it since it is not modulated at, okay, इसको हम modulated नहीं बोलेंगे. It's a modulating signal. We have to modulate it, okay. We have to modulate this guy. So this is a modulating signal, also we call it modulating signal, right? This is a modulating signal, or sometimes we call it base band signal. क्या इसको बोलते हैं? Base band signal. If you refer different books, like if you refer Taub and Ceiling, so information bearing signal you will find. Information bearing signal, right? Means message signal has got some information, right? Okay, so these are the name of this signal, right? Okay, suppose your signal looks like in time domain like this, okay, right? This is time domain, okay. Some random signal is there, right? Okay, some random signal, okay. Though we can't find the any random signal is there, okay. So basically we should find out the power spectral density of this, right? Okay, so this is a time domain signal, okay. It is not limited in time, so you need to limit in frequency. So that is called band limited. So band limitation is very important. मैंने आपको बताया भी था, you cannot do simultaneously band limited as well as time limited, right? तो ये बेसिक चीजें आपको आनी चाहिए, थोड़ा फील करो, okay, so that you can solve any question. So this is empty, so it's Fourier transform I'm going to take here, right? The Fourier transform I'm going to take, and we are going to limit that, okay. So limitation from minus w to w, right? This is f. So you can say this is nothing but mf, right? The message signal mf in frequency domain. So this is the spectrum that I'm going to consider always, right? spectrum. And now you don't think this is a triangular spectrum or something. It's a just some random waveform we have drawn here, right? And we have limited our massive signal from minus w to w. And if someone is going to ask you what is the bandwidth of this massive signal, so you have to say w, right? W, okay. You have to say w. W is nothing but a highest frequency of massive signal, right? From here to here we consider w. Okay, so always consider this, since we are talking about modulation and all as we move ahead, so we will always be focusing on the spectrum of the massive signal instead of focusing on the time domain signal. We will not consider anywhere the time domain signal. We are going to only focus on the frequency content of the massive signal, or you can say the spectrum of the massive signal. Spectrum is what? It has frequency content, right? Understood. So since if the massive signal is not properly specified, like it is sync function or any sort of other function, like actual function which some standard function, then you need to consider this kind of arbitrary spectrums, right? Okay. So this is w and this is minus w. Okay. This w is nothing but what? The consider w is nothing but highest frequency of massive signal. Right? Massive signal. Right? And this is highest means what? Highest means this is nothing but a bandwidth of massive signal. Right? Bandwidth of a massive signal, right? Okay. This much clarity you have to keep in mind first. Okay. Before you start any topic, okay, you need to have some building blocks. ये building blocks हैं. This is important for electronics, electrical instrumentation, सबके लिए important है, right? You need to understand. ठीक है. Now what you can do here is you can take ठीक है. This is important. Now you can consider the carrier signal, right? So carrier signal is what? Carrier signal. See, carrier signal is nothing but CT say we will denote CT. These are the notation that you can use it, right? Massive signal MT, okay, it has different synonym, different name. Okay, and massive signal will always be having low frequency. There is a reason I have told you. Okay, sorry for that. Carrier signal means high frequency signal, right? High frequency signal. This guy is nothing but high frequency. This guy is nothing but high frequency signal, right? So you can denote this by AC cosine 2 pi FCT. AC cosine 2 pi FCT. This is nothing but a carrier signal, right? Or you can also write this as AC cosine omega CT. Okay, like 2 pi FC. Please remember, right? If I take the Fourier transform of this, what is the Fourier transform of this guy? The Fourier transform of this guy by AC by 2 delta F minus FC plus delta F plus FC. Okay, or you can draw the spectrum also. So at minus FC, at plus FC. This is AC by 2, this is AC by 2. These are this is in F, right? This is the spectrum actually, spectrum of carrier signal. Okay. How do we get spectrum and all? I think everybody is familiar. You need to take the Fourier transform of that, right? Now, what is modulated signal, right? So whenever signal is given, right, in signal system also, whenever signals are given, you need to identify whether it is a band pass signal or a baseband signal, or so that you can play around it, right? So because they might ask whether MT cosine T is a linear time invariant. Okay, different sort of property they might ask, right? So you should know that. So suppose ST is there. ST we consider is nothing but a modulated signal. Modulated signal, right? See, before we transmit this signal, right? Actual signal MT, you can say, before we transmit a massive signal, we need to put some flavor on MT, right? We need to prepare that MT so that MT can can be transmitted successfully. Okay. I hope this makes sense to you, right? Okay, like ISRO, whenever ISRO has to launch some website, launch some satellite, they prepare hard for many years, right? And once the project is ready, they send it. Okay, carefully, right? So here in India, like whenever we communicate anything, we need to prepare first, right? So in fact, a teacher is also a good communicator, before whenever he has to plan one class. So he needs to prepare some content first, right? ऐसा नहीं है कि directly I'm delivering to you some content, right? I have prepared something, behind. Okay, so that is why in one day we can't take so many classes. Okay? So that is the reason. Fine. So this is ST. ST is nothing but modulated signal. So if you take massive signal MT and simply multiply with the you can say CT, simply multiply with the CT. So this is nothing but a modulated signal. This is nothing but modulated signal. Multiplication by massive signal, or you can say product of product of massive signal and carrier signal is called modulation, right? Okay. Understood. Please remember these points. So what is the concept of modulation and demodulation? That we have to understand, right? So what is the concept of, in general, concept of modulation and demodulation, right? That is also very important. And demodulation. Okay. And basically we have to always focus on two resources of communication system. One is bandwidth, the very first, like we are talking bandwidth from the very beginning, right? And one more aspects of discussion will be the power, right? Power. How much power it is going to consume, right? Okay, in this process. Okay, so that is also very important. So concept of modulation and demodulation, right? Suppose you have got a massive signal MT, right? This is a massive signal MT, right? So what you will do, if you want to modulate this, right? So you are going to multiply with CT. If you want to modulate this MT, I'm talking about in time domain, right? So how you will talk in time domain? The discussion should be started with the multiplication by the carrier signal with massive signal. This is the starting point. Okay, so MT is there, and you have to explain somebody that what is the concept of modulation. So what you will say, you take time domain signal, massive signal, multiply with the carrier signal XT, right? Sorry, CT here. You will get what here? You will get here MT cosine 2 pi FCT, right? Just forget about that amplitude of the carrier signal, that is 1, right? You can take here, or AC you can take, no problem. Okay. This is called modulation. And where do we do modulation? Where we perform modulation? At transmission, at transmitter, right? So at transmitter you're going to take modulation is going to take place. But at the receiver, since your massive signal is basically a low frequency signal, so at the receiver you need to recover back your massive signal, right? Okay, so what you will do, you will go for demodulation. So what is the meaning of demodulation? So demodulation will be there at receiver. Okay, so whatever you are doing, at the transmitter side, okay, you have to again do kind of demodulation such that you can get the original signal back, right? So again you have to multiply carrier signal. Here also you have to multiply carrier signal, right? So here this is a process called demodulation. So whether you modulate, okay, whether you modulate or whether you demodulate, in both cases you have to multiply with the carrier signal, guys. Now you might be thinking, sir, कैसे? ये एक बहुत ही important तरीका है, that I believe this is important to understand, right? Okay. And you have to then pass it through, after multiplication of the carrier, you have to pass it through low pass filter, because low pass filter is going to pass only low frequency signal and reject high frequency, unwanted one, right? Because after all, your massive signal is centering around low frequency, that is a baseband signal. So how do we obtain signal back from the band pass signal? Basically we'll pass it through low pass filter. Okay. So what we will do here is, suppose remember, in both cases we are multiplying what? Carrier. Okay. So let us talk, suppose MT is there, MT signal, but since in time domain description we can talk like this, okay, multiplication by carrier signal, multiplication by, you know, when we want to demodulate, okay, again we have to multiply carrier signal. So आप देखोगे when we will discuss in future different type of modulation schemes as well as different types of, you know, demodulation schemes, there we are going to perform this kind of multiplication, carrier multiplication, frequency multiplication, sorry, again demodulation case में भी we have to multiply with carrier. You will say, you will think, oh, why we are multiplying this, okay, but there is a reason behind that, we'll see, okay, but इतना आप framework याद रखो, ठीक है, so that in the gate examination at least question is, you have read the question and what they are asking, at least you can perform all these operations, because in the exam we forget everything, right? So MT, suppose MT has a spectrum of this kind, right? Okay, this is MF. In frequency domain, what we have to say, this is MF and the bandwidth is W, right? In time domain, multiplication by the carrier signal, right? When we do modulation, when we do demodulation, right? Demodulation is nothing but getting back the original signal bus. Modulation is nothing but what? Translating your massive signal to the high frequency. That is what the modulation. Okay. So MT has this kind of spectrum. So since you are multiplying here, okay, if you are multiplying this in the time domain, what is the effect in the frequency domain? There is a translation, right? So you can say this guy, entire spectrum is going to be shifted here, right? You can say FC here and minus FC. Okay, so this will be FC, sorry, FC plus FM. You can say FC plus W. Okay, first you write carrier signal, then W, and here FC minus W, right? And then you just write the mirror image of that, right? This is just a mirror image, okay? So mirror image of this, okay, you see this is at the right side, so it will be left, okay? So here minus of FC plus W. Many people are not able to find this, okay? You can say this guy is just like a mirror, okay? Mirror. You are just taking like this, okay? So this is nothing but you know, minus of FC minus W, right? Yeah, fine. If you take this minus sign inside, so this becomes minus FC minus W, and this is nothing but minus FC plus W. Okay. Understood? So left become right, right become left. Okay. Understood? Just like how you find out the mirror image of any picture. If I put, suppose this is a mirror, right? You take this guy as a mirror. So whatever picture is here, just exact replica, but like this, I say. Okay. So here, you see here the bandwidth of this massive signal is what? The bandwidth of the massive signal is something but W, right? But here the bandwidth is going to be this. Okay, if you add, it is nothing but FC plus W minus FC plus W, right? So this FC gone, so you can say 2W. Okay. So if you do modulation, so modulated signal has got a bandwidth of 2W, right? Modulated signal has got a bandwidth of 2W, right? Okay. So suppose this is K here, so this will be K by 2, right? There is a carrier also present, right? This is a carrier K by 2. K by 2 is present here. Okay. Please remember these points. Okay. I mean, there is a K by 2. This magnitude of this. Okay. There is no carrier basically present now at this point. Okay. Carrier is not there, right? Since you know, this is just a you know, amplitude of the massive signal in, you know, in frequency domain, right? So there is no carrier right now at FC. Okay, please remember, because earlier it was just a 0. Okay, 0 around, this is K. Okay, so you have to keep this in mind. Fine. So MT times CT, okay, there is no carrier at this FC. Okay, there is no particular carrier. Okay, but you need some carrier again to demodulate this, right? You need some carrier again to demodulate this. Okay, now you have sent one massive signal, right? Okay, by multiplying MT times CT. Okay, and then you are sending that signal, but you need again one carrier, right, to demodulate it. Okay, to demodulate. Okay, so what you will do here is you multiply again, right? So let me take this guy. Okay, so this is the modulation effect, right? your spectrum has got translated. But if you multiply again, so what will happen here is that, what will happen? This signal will further shifted, right? This signal will be shifted again. If you multiply with the carrier again, so this signal will shift here, and this signal will go somewhere, because that will become 2fc, right? So you have to understand, this signal will shift here and some signal will go there, and at fc there will not be any sort of signal. Okay, please remember. Okay. That is very important. So you will get this kind of a situation. You will get here something. Okay, at fc nothing will be there, but at, you can say, 2fc something will be there, right? So at 2 minus 2fc. Once you will multiply, right, you can say this is nothing but k by 2. This is k by 2 only, right? K by 2, because one signal will come from here, one signal will come from there, right? In the spectrum, once the spectrum will be shifted. Okay, since you are what can you repeat the same? What increase of bandwidth of the massive signal due to modulation is not beneficial for us now? Yes, देखो, your signal bandwidth is increasing, right? Okay, but at the same time there will be some benefit also, right? So there will be a trade-off, right? In future you will see there will be a trade-off between power and the bandwidth. So trade-off is important, right? Like sometimes what will happen, your modulation scheme is consuming lot of bandwidth, okay, at the same time consuming a lot of power as well, right? Okay, so we have to find that kind of modulation strategy or scheme which consumes less power, less energy, right? Sorry, less power and less bandwidth. आगे हम लोग देखेंगे, that is called SSB, right? Single sideband suppressed carrier, right? So that is going to consume less bandwidth, the minimum bandwidth, the minimum power. So that is why I'm talking about this, right? So as we will discuss the type of modulation, तो उसमें क्या रहेगा? In that you will find that suppose we are not happy with amplitude modulation, so we will go to double sideband suppressed carrier, right? Then if we are not happy with double sideband suppressed carrier, okay, like our goal is what? Minimum bandwidth, minimum power. My goal is what? Minimum bandwidth, minimum power, right? And that can be achieved by only one modulation scheme, that is SSB, right? But in case of SSB, only telephone, all these things are restricted, right? Okay, but as we have got huge data available, right, and the high bandwidth, we have to deal with the high bandwidth, right? So there are many strategy, right? Many techniques are there, right, to trade off between power and bandwidth. Okay, so I think this is clear, right? See, this high bandwidth is beneficial only for reducing bandwidth, reducing the height of antenna, but at the same time you're wasting your bandwidth, right? Okay, so you need to find some other alternatives. So as we move ahead, we will see. So देखो, when you will multiply cosine again with this, the cosine again you are multiplying with this signal, right? Already it is modulated signal, and you are multiplying cosine again because that is carrier signal. Again you are multiplying. Why? Because so that you can do demodulation. So again you will take the convolution of this signal, you can say band pass signal, with the impulses. Okay, so what will happen over there? So I'm saying what? So what will happen here is that signal, this guy will shift this side, and this guy will give you shift this side, right? Okay, and this guy will shift this side, this guy will shift that side. Okay, so since this and this will get added, so here you will get k by 2, but here you will get k by 4, and this is k by 4. Okay, because 1 by 2 again you will get, right? Cosine में आएगा, ठीक है? So now you have to pass it through low pass filter of a same bandwidth, you can say. So you will get here or more bandwidth, you can say, ठीक है? You pass this guy with the low pass filter. You will get original signal back. Okay, I think this is clear, right? So I believe this is fine. This is very important concept that I wanted to talk. Okay. But graphically कैसे देखो, ये तो just normal discussion है, right? It's a mind map that I have told you before, how to perform modulation, how to perform demodulation, right? But we need to introduce the block diagram, okay, so that we can keep in mind always, right? So this product is nothing but a product modulator, you can say, right? We sometimes call it product modulator. How does our product modulator look like? So we will take this empty here, right? And we are going to put this, this is nothing but a modulator, you can say product modulator. Okay, this is a modulation that is happening. So you are multiplying same thing with the local oscillator is generating here the carrier signal. Okay, this is the transmitter end. Okay, simple, right? And this is going to be your antenna, right? You take the massive signal, and this is nothing but a local oscillator. Okay, this is generating high frequency carrier signal, right? And you're multiplying, that is called product modulator, right? So here you're getting empty times CT, right? You can say here you're getting kind of ST. Okay, here you're getting kind of ST. ST is nothing but product of empty times CT, right? That is a modulated signal. That is a modulated signal. Now what you do here is, at the receiver end, right? This is, suppose there is a receiver end, right? So again you have to introduce what? Modulator. तो यहाँ पर क्या करेंगे? Again you will multiply with CT here, and then you have to pass it through LPF. Okay? And this is the actual signal that you will get, right? Okay, so this job is going to be done at the receiver end, right? So always you will find that whenever you are talking about any sort of receiver, so there will be a low pass filter, right? Okay. So CT, you need CT to also send along with the massive signal, right? So that that CT will be multiplied there, right? Okay. So this is very important. So let me do mathematics also. So this is the block diagram that you have to keep in mind. Okay, basic block diagram that I have told you. So suppose you have got you have got empty and you have got CT. You modulated it, right? So ST you got, ST is nothing but empty time cos 2 pi f CT, right? So that is ST. Now at the this is at transmitter end. At the receiving end, what will happen? You need to have this ST, right? ST times cosine 2 pi f CT, right? Means you have got this ST is nothing but a modulated signal. Remember, this is modulated signal. Okay, this modulated signal has passed through the channel. Okay, now this guy has reached at the receiver. Okay, now you need to multiply this ST with carrier signal again. So, see, we are just considering carrier signal amplitude is 1, right? You can consider AC also, just to eliminate disturbances, to eliminate complexity in the mathematics. I'm just taking AC equal to 1. You can take AC equal to AC only, right? No problem. And we are also not considering the phase, right? Remember, the phase also we are not considering, but that phase is also important. See, carrier has got 3 things: amplitude, frequency, as well as the phase, right? But we are only considering here the frequency, right? Okay, but everything has to be there, right? If you multiply this, so you can say that here empty cosine 2 FCT times cosine 2 FCT. Okay, so simple, this is what you can say: empty times cosine square 2 pi FCT, right? So what is this cosine 2 pi? So empty times, I think anybody can write this, 1 plus cosine 4 pi FCT by 2, right? Okay. So further, if you resolve this, so it is empty by 2, okay, plus empty times cosine, right, 4 pi FCT by 2, right? Okay. Okay, so this is what the receiver, at the receiver, okay, before the low pass filter, right? This is the expression that you will get. Okay, cosine square theta, you can say. Okay, yeah. Okay, it was 2 pi FCT, so it became 4 pi FCT. That's it. Now you need to pass it through low pass filter. So low pass filter में क्या होगा? This guy will be रिजेक्टेड, ओके, बिकॉज इट इज एट हाई फ्रिक्वेंसी। तो ये आ जाएगा आपको। तो यहाँ पर क्या आएगा, mt/2, and this 1/2 can be adjusted, okay, with the help of some sort of amplifier gain or something. You can adjust that 1/2, right? Okay, so you'll get original signal, right? Understood? So this is the process that going on, right? Hmm? So in frequency domain, what is the definition of modulation? In frequency domain, if I talk about frequency domain, so modulation, definition of modulation is nothing but what? Definition of modulation is nothing but translation, right? In simply a frequency domain, translation, frequency translation. Okay. But in time domain, what is the definition of what is the definition of modulation? That we have to understand. Okay, that is very important. What is the definition of what is the definition of modulation in time domain? Okay, when you multiply mt into ct, that is important, and I think you might be waiting for that only. Okay. So याद रखना, it's a simple process. Okay, okay, till now I did not specify whether it is a amplitude modulation, whether it is a DSP modulation, double sideband, okay, double sidebands, okay, all the, I did not talk about band, in fact, right? Okay, but you have to understand, if I go back, okay, if I go back, since you are doing, since you are doing modulation here, so this is basically a upper sideband and this is the lower sideband, we call it, right? From fc to fc plus w, we call it upper sideband, okay, because there are two bands, upper sideband, lower sideband, okay. So upper sideband, lower sideband, so we call it double sideband. There are two bands now, so double sideband, okay, but most of the information is contained in upper sideband only. You see here, if you look at the original message spectrum, so here the most of the signal information is contained in upper sideband, right? So this is the upper sideband. It has got translated to high frequency, right? So and this is just a replica of the information that we have, right, in the negative frequency. Okay, so please remember all these things. There is a upper sideband. What is the range of upper sideband? What is the range of lower sideband, right? So upper sideband is nothing but from fc to fc plus w. Lower sideband is nothing but from fc minus w to fc. Okay. So this is the story, okay, mathematics, okay, that mathematics, you have to perform at the receiver, at the receiver. Please remember this. I think this is clear for all. Now, what is the definition of modulation in time domain? See, since you are multiplying mt into ct, right? Okay, product of mt into ct. Okay, so process in which parameter of the carrier, right? In time domain, what is the definition? This is the definition that you have to tell, okay, to people whenever they will ask, right? So in time domain, the definition is going to be the process. Modulation is just a process, you can say, process. Since you are multiplying any time domain signal with a cosine, right? Like mt cosine 2fct. Let me write all carrier parameters. So mt times ac cosine 2fct. Right. Any message signal you take, any message, you can take some known standard message signal also, right? You can take I will take a decaying exponential I'm gonna take, right? Or so you will see that. Okay, but I'm going to focus here on in time domain, right? I'm not going to focus on frequency domain now, because you know what is going to happen in the frequency domain if you do modulation, right? I'm not particular about modulation at this moment. Like, I'm not talking about any sort of like whether there is a amplitude modulation or frequency modulation or a phase modulation. I'm going to focus on the parameter of the carrier. There are three parameters of the carrier that you have to understand. So carrier amplitude, AC cos 2 pi fct, right? So this is ct, and this guy is called amplitude, this guy is called frequency, and there is a one more guy which is called phase. इसको बोलते हैं phase. So you can have three sort of modulation: the amplitude modulation, the frequency modulation, the phase modulation, right? So 100% 4-mark question you can obtain from analog. Like from FM, one question is certain in the gate examination, right? Or from amplitude modulation also one question you can expect. Okay. But whatever math we are doing, these maths you have to perform in the gate examination, right? Don't look at the question and wait, okay, what will be the answer for that? Whatever instruction is given in the question, you have to perform it, right? Whatever block diagram is given in the question, you have to go in the flow, right? From input to output, you have to go. Whatever operation you have to perform mathematically, you just perform it. And suppose you have to pass it through LPF or band pass, you should pass it. Okay, why you're waiting for somebody, right, to pass it and get the answer, right? Don't leave, don't attack to the question directly. Okay, option A is correct. Don't guess it, okay? Because most of the question will be asked from like MCQ question from this, right? So MCQ question has negative marking. Okay. Yes, according to the message signal, you should say, right? It is a process in which it is a process in which a parameter, any one parameter, you can say a parameter of the carrier signal, meter of carrier signal, right? A parameter of carrier signal okay varies according to the message signal, right? Okay, this is important fact that I will be continuing from the next session, right? So I hope this makes sense to you, right? So please remember, I will talk about these things in the next session, right? Because already the length of the session should not be more, otherwise other people cannot watch it. I just want I hope I tried well to explain you what is modulation, right? और आपको थोड़ा सोचना है माइंड में, माइंड मैप यू जस्ट क्रिएटेड, ओके, message signal, time domain. Okay, so talking about modulation in frequency domain is very easy. Okay, and talking about the time, modulation in time domain looks difficult, but it is very easy, right? Please remember. So I will meet in the next session. Thank you so much for right now. Thank you.